All right, so hey everyone, welcome back to our final session. Okay, so we've covered all of our required material for this module. However, there's often this recurring question that comes up during our live sessions with regards to how do we determine whether predictors are statistically significant, or even our overall model. How do we determine our model is significant? So this optional material extends on statistical inference, specifically going over hypothesis testing within linear regression. And I just want to reiterate the fact that this is optional material. So if you're not interested, that's totally fine. You can use this class as a work period to complete your remaining assignments. However, for those of you who are interested, we're going to talk about hypothesis testing today. So for this material, we really have three main learning objectives. The first one is going to be understanding hypothesis testing in linear regression. So specifically defining and interpreting the null hypothesis and alternative hypothesis within the context of a linear regression. And then we're also going to discuss statistical tests for individual beta coefficients known as t-tests, and then also statistical tests for overall model significance using the f-test. And then lastly, we're going to be performing hypothesis tests to evaluate the significance of individual regression coefficients, including intercepts, and assessing overall model fit within Python. So the second half of the course, as usual, we're going to turn over to our Jupyter Notebook. And just to note that this content is under O4, this cohort in terms of on the Git repo, just because it is optional material. So I'm just gonna put the link to the slide deck and the notebook for those of you who are interested in the chat. Okay. So, hypothesis testing is a really powerful method that helps us draw conclusions about a population using sample data. So, it allows us to determine whether the data that we observe provides enough evidence to support or reject a particular claim. So, within the context of linear regression, it can answer questions like, is there a relationship between two variables? So, for example, does the size of the house in Sacramento, is it related to sale price? So by setting up hypotheses and testing them systematically, we can decide whether these relationships that we see are statistically significant or are they just due to random chance. So when conducting statistical inference, we're comparing two competing hypotheses to guide our decision making. And the first one is called the null hypothesis, or HO, as shown here. Oops. So this represents the default or the baseline assumption. So it often represents no effect, no difference, no relationship. So for example, suppose we want to test if the size of a house in Sacramento affects sale price. Our null hypothesis in this scenario would be that there is no relationship between house size and sale price. And this means that, in other words, the size of the house does not influence the price of the house. We also have the alternative hypothesis, or H1, and this contradicts the null hypothesis and aligns with our research interests. So here it posits that there is an effect, or there is a difference, or there is a relationship between these two variables. So once again, going back to that house size, house price example, the alternative hypothesis would be there is a relationship between house size and house price. So that means a change in house size would correspond to a change in sale price. So to solidify this concept with another example, imagine you're a coffee shop owner trying to decide whether a new type of coffee increases customer satisfaction compared to the current one. The null hypothesis would be something like the new coffee does not increase customer satisfaction. In other words, customer satisfaction scores with new coffee are the same as the current one, so there's no change. The alternative hypothesis would be that the new coffee increases customer satisfaction. And this means that customer rates the new coffee higher than the current one. So what's important here is that we do not prove the null or alternative hypothesis outright. Instead, we evaluate the evidence. So if the data are inconsistent with the null, we reject it in favor of the alternative hypothesis. So for example, if our statistical analysis showed a strong relationship between house size and sale price, we would reject the null and conclude that there's evidence for a relationship. Once again, going back to this coffee example, if we were to reject the null, this doesn't mean that the new coffee is guaranteed to improve customer satisfaction, but it would mean there's strong evidence in favor of that. Alternatively, if the data are consistent with the null hypothesis, we do not reject it. So for example, if analysis yields a non-significant relationship, that would mean we fail to reject the null and we conclude that we don't have enough evidence to support a relationship between house size and house price or the new coffee and increased customer satisfaction. So the key idea here is that failing to reject the null is not the same as proving the null is true. It simply means that the data we have do not provide significant or sufficient evidence against it. So as a reminder, this is the equation for a line for simple linear regression. So we have y is equal to beta naught plus beta 1x, where here y is our response variable, beta naught is the vertical intercept or the y-intercept, beta 1 is the corresponding slope, which tells us how much y changes per each unit increase in x, and then x is our predictor variable. So together, beta naught and beta 1 define this line of best fit that we talked about a couple sessions back. So this straight line minimizes, once again, the error between our predicted values of our response variable and what the actual values are. So this slide should be review. So going back to the example data set that we used with linear regression, we're going to now illustrate how hypothesis testing can be applied in practice. So first, let's consider this really simple question of, is there a relationship between the size of a house and its sale price? So to answer this, we use hypothesis testing in the context of linear regression. So specifically, we examine the regression coefficient, so these beta values. So the regression coefficient for house size would be denoted as beta 1, as we talked about. And here the null hypothesis would be beta 1 is equal to 0. This would mean, in other words, there's no relationship between house size and house price. So in other words, the slope is 0. The house price doesn't change per each unit increase in house size. We also have an alternative hypothesis where beta 1 does not equal 0. In other words, there is a relationship between the size of the house and the price of the house, whether that be positive or negative. So essentially, once again, we have these two competing hypotheses where null is that the beta coefficient is equal to 0, and the alternative is that the beta coefficient is not equal to 0. In other words, the null is saying that there's no relationship between our predictor and response variable, whereas the alternative hypothesis is that there is a relationship between predictor and response variable. Does anyone have any questions so far? Maybe just a thumbs up if everyone's okay, and we can continue. Okay, great. So, oh, yeah, there's a hand.
I'm just wondering, so yeah, I'm familiar, this is part of statistical. Is this similar to, mathematical, like you have induction where you try to prove, but the way you prove it is you fail to prove, and that's how you conclude a mathematical logist. I don't know, I studied in high school mathematical induction. Is it a similar concept or they're two different?
Yeah, so here we're not proving the null, we're just either failing to reject it. So those two things aren't necessarily the same. We don't accept the null, we just fail to reject it. So our data doesn't have sufficient evidence to reject it. It's not the same thing as accepting the null. So the wording here is a bit different.
Sure. So do we still use these null hypothesis, alternate hypothesis in the, I know it's a part of statistical learning, but in the regular machine learning, either linear regression or we use in the industry or this
In predictive modeling, not as much. This is more inferential modeling. So we went over predictive modeling where we were looking at like accuracy within linear regression. This is asking a statistical inference question. So is there a relationship between two variables?
Right. If
is
so,
that
which one is actually
relationship
positive? Yeah,
statistically significant? So
like you were
depending
saying,
on the
right?
question you're answering. So yeah, so the very first class we talked about predictive modeling versus inferential modeling. So that's where we're talking now about statistical inference.
Okay. So let's say in the medical healthcare, right? So let's
Yeah.
say we found, I don't know, COVID positive or whatever. But if you want to say which actually caused out of these, whatever the uh, parameters or features, so this would help, I guess, right? Instead of just
Yeah,
saying,
so this would allow us to determine which predictors are statistically significant, yes. Whereas in the predictive modeling, we were just getting an overall accuracy measure, but we weren't seeing, especially if we have multiple predictor variables, which ones are significant.
right, in a bank, right? For example, if you just reject a mortgage application, that doesn't suffice, right? You rather have to specify what caused that rejection or approval of a loan, something like that, right?
Yes. Hmm.
So thanks.
Yeah, no problem. Yeah, there's another hand up.
Yeah, sorry, I didn't go through the notes before, so I just was curious. We will be going through the frequentist way of, testing the hypothesis, or will be going for the Bayesian way? Because I know that most of the statistics, like people do like the frequentist approach, where you are looking at the mean variance sort of thing, like a t-test, for example, right?
We're doing a t-test, yeah, for
Okay.
individual beta coefficients, and then an f-test for overall model fit.
All right. So because there's also like a Bayesian approach, right? So it's like we have a prior probability, and then we can update the prior based upon evidence sort of approach. So it seems like people are more favoring the Bayesian approaches these days, because the other approach can be, there's be a lot of what do you call it, the error can be a problem sometimes, right? The significance and all that stuff. So okay, I just wanted to know that, like,
Yeah.
what would be our
Yeah, we're
approach here.
starting off with the very basics this time around. So yeah, we're just gonna start off with regular like t-test, f-test, and then yeah, there's more advanced topics with regards to Bayesian. Yeah.
Cool, thank you.
Yeah, no problem. Okay. So when we include categorical variables as predictors in a regression model, interpreting the beta coefficients requires a slightly different approach compared to continuous variables. So just to get everyone on the same page, we talked a bit about this in prior sessions, but categorical variables are variables with distinct groupings or categories. So for example, biological sex as male or female, particular region, education level like high school, college, etc. And as we learned in these prior classes, when we're dealing with categorical variables, they're converted into dummy variables, where one category is chosen as a reference, and then the remaining categories are basically compared to it. So in this situation, the beta coefficient, once again, tells us the impact of each category relative to the reference category on the response variable. So going back to our housing data, looking at categorical predictors, housing type, when predicting house prices. So here, for example, the house type can be one of three categories. So it can be a condo, it can be a residential home, or a multifamily home. So let's say residential home is our reference category. This would mean that all other house types, so condo and multifamily, are compared against the residential type. So the reference category does not have its own beta coefficient, but once again, it serves as the baseline. So our equation, as we saw in the class prior, would, for example, be the beta naught representing the intercept plus beta 1, which would represent, for example, condos, and then beta 2 would represent multifamily homes. And when we're interpreting these beta coefficients for this categorical predictor, here the intercept represents the average house price for a reference category. So here, the average house price for a residential home. And then beta 1 shows how much the average price for condos differs from residential categories. So for example, let's say beta 1 was minus $50,000. That would mean that condos are on average $50,000 cheaper than residential homes. And then we have beta 2, which is multifamily. And this once again shows the average price for multifamily homes compared to residential. So for example, if this beta value was $30,000, this would say that multifamily homes are on average $30,000 more expensive than residential homes, which are a reference. So really the key thing here to note is that we're comparing to a reference group, and this provides us with a baseline for this comparison. So the beta coefficients, once again, are showing how much higher or lower the price is for one category compared to this reference group. So that's how you would interpret it in terms of categorical variables. Okay, so we have these oh, yeah, Kevin?
I think that is the like when we did this one hot encoding or categorical, right? I think I
Exactly.
remember very well.
Yep.
The problem with the dummy variables, right? Like you said, a condo, residential, multifamily.
Yeah.
That doesn't mean I think that's a drawback. That's why we use the one hot encoding, because in the dummy variable, when you say uh, that magnitude or a difference between a condo versus multi versus the family, I think
Yeah.
it's not exactly equal. That's why I think we use the one hot, not the dummy variable. I remember that part, encoding when you encode the right.
Yeah, so that's one hard encoding is how you get these dummy variables. So it gives you a reference at the end.
I thought they're two different because dummy variables is like a 001 or 100, right? That's how you use. Oh, that's maybe I'm wrong. I think. I remember.
No, so this is remember we did the one hot encoding, so we were able
Right.
to remove one type, and then that one type we removed is considered a reference category. So when we have these remaining beta coefficients for condo and multifamily, we don't have one for residential, although the intercept one would be the average house price for this reference category. But these ones are then being compared to this reference group that we sort of removed from the equation.
Cool.
Yep. Okay. So we went over these hypotheses. So now we have them. And the next question becomes, okay, how do we test them? So when testing the null hypothesis for the regression coefficient, for example, beta 1, we need to determine whether or not it is sufficiently different from 0. So this is done by calculating a t-statistic, which helps us assess whether this estimated coefficient for the predictor is significantly different than 0. So here, once again, the null hypothesis would be that this coefficient is 0. So we're comparing the predicted value to the null, so to 0. So here's how we calculate the t-statistic. And just to orient you with regards to the annotation, you'll notice that there's this little hat on top of the beta 1 coefficient. And this just refers to the fact that this is an estimated value for the regression coefficient beta 1. So this hat basically just implies that this is estimated based on our data. And they're estimated because in statistical modeling, we rarely know the true values of a parameter. So we rarely know the actual values of beta 1 because we don't have access to the entire population data. So here we're only working with sample data, and such these parameters that we calculate are estimates based on that particular sample. Okay. So we have beta 1 hat here, and this is the estimated beta coefficient for a predictor. So for example, house size. And this is the value that we compute based on the data we have. We also have the standard error for this beta coefficient, and this measures how much the estimated coefficient might vary if we took different samples from the population. And then once again, we have this value of 0, and this is the value under the null hypothesis, which assumes that there's no effect. So this computes a t-statistic. And the t-statistic, once again, tells us how many standard errors the estimated coefficient is away from 0, which once again, 0 is the value under the null hypothesis. So if the t-statistic is large, it would suggest that the beta coefficient that we computed is far from 0, and this provides us with evidence against the null hypothesis. So in other words, there's evidence of a relationship between the predictor and the outcome. However, if the t-statistic is small, it suggests that this beta coefficient is close to 0, meaning that there's not enough evidence to reject the null. In other words, there's no significant relationship between our predictor and outcome variable. So now that we can know how to calculate the t-statistic, we need to determine what exactly is far enough from 0 in order to reject the null. So here we compare an absolute value of the t-statistic to a critical value from the t-distribution table. In simple terms, when we're performing null hypothesis testing, we want to know whether our results are significant enough to reject the null hypothesis. So we have this critical value, and this is sort of like a boundary or a threshold that helps us decide this. So you can think of a critical value as a point that helps us decide whether our test results are far enough from the average to be considered unusual or significant. And if our results are beyond this threshold, we conclude that there is a meaningful effect. If it's within this usual range, we say that the effect is not significant. And there's two main things that affect this critical value or this threshold. The first is the sample size. So sample size is once again how many data points or observations that we have in the study. So larger samples give us more reliable estimates of a population. And so we would need a smaller critical value to declare that something's significant. On the other hand, smaller samples make us more cautious. So in this case, we would require a critical value or a threshold to be larger. There's also a significance level. So this is often denoted by this alpha here. And the significant level is just the number that we choose before starting the test. We usually set it to 5%. And this means basically that we're willing to accept a 5% chance of making a mistake, meaning a false positive. So as we've learned, this is saying that there's an effect when there actually isn't. So once again, the significance level is often set to P of 0.05 or 5%, meaning that we're willing to accept a 5% rate of a false positive. And then depending on our sample size, we either need a larger or smaller critical t-value that we're comparing our. So once again, the critical value is corresponding to the graph, the point in the graph where 5% of the area is on the extreme tail, which we're going to see, I believe, the next slide. Okay, let me just check the chat really quickly. Yes, so here our estimated values are the same as what we're predicting, yeah. So just like the bell-shaped normal distribution we talked about last class, the t-distribution is a type of curve that helps us make decisions in statistics. So it plays an important role in hypotheses testing, especially when we're working with smaller sample sizes. And the t-distribution looks really similar to a normal distribution, but it has these flatter tails at the end. And what this means is that with smaller samples, we're expecting more variability and uncertainty in our estimates, which is why we have these flatter tails. So when we're testing hypotheses, we need to figure out how far away our test result is from zero to decide if this is something we should pay attention to. Is it unusual or significant? And the t-distribution helps us do that. So to decide whether our coefficient is significantly different from zero, we compare our t-statistic that we calculated to a critical value or this threshold from the t-distribution. So once again, this critical value is this cut point or this threshold on the t-distribution that tells us if our results are far enough to reject the null hypothesis. And if our t-statistic is greater than the critical value, it means that our results are unusual enough that it's probably not due to chance, so it's significant. If the t is smaller, we would say that the results are likely due to chance and we don't reject the null hypothesis, or we don't have enough evidence to do so. So the figure here just shows us how the t-distribution is used to determine whether we can reject the null hypothesis based on our test results. So the curve you're seeing once again is this t-distribution, which shows how values like our t-statistic are spread out. And just like a normal distribution, it has this peak at zero, but the tails once again are wider just to account for more variability, especially with smaller samples. We also have this red dashed line here. And this, for example, is representing the t-statistic that we computed based on our data. And this is the value that we're trying to compare to the critical value to decide if we can reject the null hypothesis or not. If this t-statistic that we calculated is very far from zero, it suggests a significant effect. But if it's close to zero, it would suggest no significant effect. And here, this red shaded area is called the rejection region. And this represents the extreme values on the tail of the distribution, where we would reject the null hypothesis. So if our t-statistic falls within this rejection region, we say that our result is significant and that the relationship between the predictor and outcome is likely not due to random chance. So the critical value here is this point where our t-statistic would be considered large enough to be within this rejection region. And if our calculated t-statistic exceeds this critical value, it would fall into this rejection region and we would reject the null hypothesis. So as we've learned in regression, we don't have to stop at just one predictor, and we can extend our model to include multiple predictors, which may be helpful in understanding relationship between an outcome and several factors simultaneously. And by including more variables in the model, we can perhaps capture more variability and complexity, potentially improve our predictions. So for instance, let's say we not only want to predict house price based on size, but also now the number of bedrooms. So this model will become y. So the y is our response variable or house price. And then we have our intercept of the model. And this, once again, is the estimated house price when both predictors, so here house size and then number of bedrooms is equal to 0. We have beta 1 then, and that's the slope for our first predictor. So for example, let's say it's house size, and this tells us how much house price changes per each additional unit increase in house size, holding the second variable, number of bedrooms, constant. And then we also have this beta 2, and this is the slope for the second predictor, number of bedrooms. And this is telling us how much house price changes with each additional bedroom, holding the house size constant. So when we add multiple predictors to our regression model, the process of hypothesis testing basically remains the same as it did with the single predictors. We perform separate t-tests for each beta coefficient to determine if it's significantly different from 0, which we would indicate that that particular predictor has an effect on the outcome. Once again, the null hypothesis is that for each predictor, we assume that there's no effect, so to 0. So for example, here we have the null being the first beta coefficient is equal to 0 and the second beta coefficient is equal to 0. This would mean that house size has no effect on house price, and then this would mean that number of bedrooms has no effect on house price. Alternatively, we have the alternative hypothesis that is basically the opposite of the null, suggesting that the predictor does have an effect on the outcome. And this would mean that the regression coefficient or the beta coefficient is not equal to 0. So here, for example, beta 1 not equal to 0, meaning that house size does have an effect on house price. Beta 2 not equal to 0, that would mean the number of bedrooms does have an effect on house price. And similar to what we saw before, we basically just perform a t-test for each of those beta coefficients separately to test whether this particular coefficient is significantly different from 0. And once again, if the t-statistic is large enough, as we saw earlier with the t-distribution, we reject it under the null hypothesis and conclude that that particular variable does have an effect on outcome. So in this case, on sale price. However, if the t-statistic is not large enough, we fail to reject the null, and this suggests that the predictor does not have a significant effect on the outcome, in this case, sale price. Okay, does anyone have any questions? Are we okay so far? Okay, great. All right, so we talked about the t-test, and the t-test is helpful to assess significance of individual predictors. However, we also have the f-test, and this is used to evaluate overall model significance when we have multiple predictors. So the f-test is basically telling us whether the model as a whole is better than a model that would include no predictors, just the intercept. So in other words, the f-test is evaluating whether a set of predictors together significantly improve a model compared to a simple model that has only the intercept and no predictors. And this is important because sometimes individual predictors might not show a significant effect individually, but together they might explain a substantial amount of variance within our response variable. So I keep saying in comparison to an intercept model, and what this is saying is this is just a model that would predict the average value of the response variable. So the average house price, for example, across all observations without any predictors. So for each individual listing, it would just predict the average house price within the data set. So we're saying, is this model with these predictors better than a model that's just predicting average house price? So once again, the F statistic is comparing the model with full predictors to an intercept-only model. And the null hypothesis would mean that the model with predictors is not significantly better than an intercept-only model. This means that the predictors together have no effect on the outcome. Alternatively, a model with predictors could be significantly better than an intercept model, and that's what the alternative hypothesis is suggesting. So this is saying that at least one of the predictors explains a significant amount of variation in the outcome. So similar to the t-test, if the F statistic is large enough, we reject the null hypothesis and conclude that the model with predictors is significantly better than an intercept-only model. And this would indicate that at least one of the predictors has a meaningful relationship with the outcome. So the F statistic, once again, is comparing two models. It's comparing this full model. This is the regression model that includes predictors. So for example, here we have this model, and let's say it includes predictors as house size, number of bedrooms, and then neighborhood, for example, these three predictors. And then we have a reduced model. This is a simple model, not including any predictors, just the intercept or the mean value for the outcome variable. So for example, here a model would just predict the average house price for all houses without considering any other factors. So it doesn't consider house size, number of bedrooms, etc. So the F statistic, once again, is telling us whether this full model predictors with predictors is significantly better than a model that only has the intercept. In other words, it tests if the predictors in the model provide us with useful information to explain the variations that we're seeing in our outcome variables, so within house price. So the F statistic is essentially a ratio that's comparing how well the full model explains variability in our response variable, so in house price, compared to how much variability is left unexplained. So the explained variance here, this is the proportion of variability in our response variable that's explained by our predictors in the model. So in other words, how much of change in house price can be explained by these predictors like house size, neighborhood, number of bedrooms. Then we have this unexplained variance here, and this is the variability in our price that cannot be explained by our predictors. So this is, in other words, the residual or the error within the model. And this is the part of house price that is still left unexplained after accounting for these predictors. So here the F statistic is this ratio. It's calculated as explained variance over unexplained variance. And if an F statistic is large, it would suggest that the full model with predictors explains a significant proportion of variability within our response variable. And in this case, we would have evidence against the null hypothesis, indicating that the model with predictors is significantly better than a reduced model, which would just predict the mean value of price. In other words, the predictors are doing a good job at explaining the variability in house price. However, if the F statistic is small, this would indicate that the full model does not explain much more variance than the reduced model. And this would suggest that the predictors have little effect and that predicting just the mean value of price would perform just as well. In other words, the data are consistent with the null hypothesis, meaning that the predictors do not improve the model significantly. So how do we determine now whether our F value is sufficiently large? And this approach is really similar to a t-statistic approach, where to determine whether it's large enough to reject under the null hypothesis, we compare it to a critical value, this time within the F distribution table. And this value, similar to the critical t value, is dependent on sample size, where once again, a larger sample generally provides more accurate estimates and variance, and leads to more reliable conclusions, so we wouldn't need as large of a critical value. Also, significance level. So typically, once again, we set our significance level to 0.05, which means that we're willing to accept a 5% chance of a false positive. So if the calculated F statistic exceeds this threshold or this critical value from the F distribution, this would give us enough evidence to reject the null hypothesis. And this means that we have evidence to support the conclusion that the full model, which includes our predictors, is a better fit for the data than a model with no predictors at all and just the intercept. So the F distribution, once again, is commonly used to compare how much better a model fits the data compared to a simpler model. So the F distribution has this really long tail on the right side here, and this means that the majority of the values are clustered around 0. But there's this possibility of a very large value. And the F statistic can never be negative, because if you remember, the F statistic is this ratio of explained variance versus unexplained variance. And since variances are always positive, the F statistic as such is also always positive. So this figure here is representing the F distribution curve, which is used to assess, once again, model significance of the full regression model compared to a simpler model. So the F distribution curve is, once again, this bell-shaped curve, but it's right skewed, meaning that the majority of the values are clustered towards 0, or the left side of the chart here, but there's this long tail stretching right. And this long tail indicates that larger values of F are rare. So this red dashed line here in this case is representing our F statistic from our regression model, let's say. And its value is what we found from the model. So it's computed from our data. And we're comparing what this F statistic that we computed to this critical value from our F distribution table. And if the F statistic falls to the right of the dashed line, it suggests that the model significantly explains an amount of variance and gives us evidence against the null hypothesis. And once again, the shaded area here would represent our critical region of the F distribution, or our threshold, and this is where large values of F are located. So if our F statistic falls within the shaded region, it would allow us to reject the null hypothesis and conclude that the full model with these predictors is a better fit for our data compared to the model with no predictors. And this critical value, once again, it can be thought of as like this boundary that separates our rejection region from our non-rejection region. And if the calculated F value exceeds this critical value, we're able to reject the null hypothesis. So going back to our house data, imagine we're comparing whether how well the model fits the data. One model is very basic, no predictors, just predicting the average house price regardless of anything. And then we also have this more complex model with predictors like house size, number of bedrooms, neighborhood, whatever. If the F statistic falls within this critical region, it means that the full model is significantly better at explaining the data than the simpler model. However, if the F statistic falls outside of this critical region to the left, so here, we don't have enough evidence to reject the null hypothesis. And here we would conclude that the full model does not significantly improve our ability to predict house price. So we would fail to reject the null, in other words. Does anyone have any questions about this? So we went over 2 different tests. We went over the t-test for individual beta coefficients and also the f-test, and that's how we determine overall model significance. Yep, there's a hand.
How is the t-test different from the R-square value? I mean, even R-square is trying to arrive at a similar
Yeah, they're
conclusion.
similar. So R-squared is saying the proportion of variance in the response variable that's explained by the predictor. However, the t-test is what we're comparing to a null so here we have hypotheses. So we have the null hypothesis that we're trying to either reject or accept. So we're determining whether this value is statistically significant. So that's why we're doing this t-test. So I remember, I believe some of the learners were saying, okay, is an R squared of 0.5 good? Is it bad? Is it significant? And we can't actually determine whether the R squared is significantly statistically significant, but we do these tests, like for example, the t-test or the f-test, to determine whether overall model fit or individual predictors are statistically significant. Does that make sense?
So this is what I understand.
Mm-hmm.
Correct me if I'm wrong.
Yeah.
So the t-test will tell me if the variable is statistically significant with respect to the y,
Yes.
and R square will tell me how much of the variable is explained by.
The overall model, not a particular variable, the overall model. So how much variance in y is explained by the model.
So if I calculate a correlation between R square value between two variables, let's say y and some x1,
Mm-hmm.
it would explain how much of y variance in y is explained by. It would tell how much of variance in y is explained by x1, right?
Yes.
And if I run a t-test between the two, I would know if there is any relation or not.
If it's statistically significant, yes.
Clear.
Yep. Yeah, Omar?
Yeah, Julia, just quick question over here. I think you've discussed it before or explained it multiple times. I do apologize for this, but
Yeah, no
how
worries.
do we kind of differentiate or say that there is a correlation versus there's a relationship or like causality, dependency? I'm talking about the second point over here when it says independence and meaning no correlation. So how do we usually find out that there is a correlation versus it's caused by that kind of factor?
So this is basically saying that we're assuming that, just jumping ahead a little bit, but it's assuming that the data points aren't correlated. So this is more so built into the data, depending on how the data is actually collected. So for example, here we're basically saying data points representing individual houses. One price of a house does not necessarily influence another price. And we typically do have independence assumed within our data sets. It becomes a little bit more tricky when we have time series data, for example, and that's where this assumption of independence might be violated,
Okay.
if that makes sense.
Kind of. Yeah,
Okay.
right. Thanks.
Yep. So maybe it'll make a little bit more sense when I go over this particular slide. So the idea here is that before you run a regression model, it's important to test certain assumptions to ensure that the results are valid. Because if you're performing a linear regression and these assumptions aren't met, you would still get an output, but perhaps they won't be valid. So let's go over some of these assumptions. So we have this assumptions of linearity. So this is the idea that there should be a straight line relationship between the predictor variable and the response variable. A really easy way to check this is just simply plot the data. So specifically a scatter plot of X and Y. And if the points are roughly forming a straight line, this would suggest that the linearity assumption holds true. We talked a little bit about this idea of independence, and this is that the data points themselves should be independent of each other, meaning that there's no correlation between errors or residuals. And this assumption, once again, as I talked about a bit earlier, is built into how the data is collected. So for example, data points representing individual homes, if the price of one house doesn't influence the price of another, independence in this case is assumed. And then I gave the example of time series data. We would need to check for autocorrelation in this particular instance, just because of the fact that time series data is often correlated. Also, this assumption of no or little multicollinearity. So in multiple regression, meaning we have more than one predictor, these predictors should not be highly correlated with each other. And to detect multicollinearity, we can use techniques like the variance inflation factor, or VIF. We discussed this in a prior section. It's beyond the scope of this particular module. But basically, the idea is that a high VIF suggests that two or more predictors are highly correlated with each other, and this could potentially cause a problem in estimating their individual beta coefficients, leading them to be unstable. So these are all assumptions that need to be met before running the model. However, once you fit the regression model, it's important to test other additional assumptions. And these are assumptions that ensure that your model is reliable, that the results are valid for hypothesis testing. And these include things like homoscedasticity, meaning that the spread of the errors should remain constant across all values of the predictor variable. This means that the variability of the residuals shouldn't change too much as the value of X increases or decreases. So for example, after fitting a model and you plot the residuals, so you plot the errors against the predicted values of Y, if the spread of the residuals looks roughly the same, so there's no specific patterns, this would mean that the assumption of homoscedasticity holds true. So for example, what I mean by this is that there shouldn't be larger errors for example, larger house sizes. So there shouldn't be this funnel where the residuals are increasing as house price increases. The error should be roughly evenly distributed, and there should be no patterns. Also, the idea of errors or residuals should be approximately normally distributed. So, yeah, Antonio?
Yes, one question. I understand in the homoscedasticity, sorry, I mispronounced it. You know what I mean?
Yeah.
When the first statement I get it, the spread of errors across X.
Yeah.
But then when it says that you can plot the residuals against predicted Y,
Yeah.
shouldn't we plot the residuals against X? I didn't get this part.
You can do, I believe you can do against the predicted values, or you can do Y, X or Y. Let me see, hold on. Yeah, so this is against Y. So typically you could, but people have done also against X as well. And we'll go to that in the next slides shortly, just to give you an overview of what it would look like if homoscedasticity is met in the plot coming up.
Okay, I will wait. Yeah, I don't get it. Thank you.
Yep. Yeah, Omar?
Yeah, Julia, just a question. Can you give us the reference to which chapter this in the book? I can't remember the name of it. The learning statistics, I guess, from Python. Let me just get you the name of
I
the book.
don't have it offhand, but I can definitely send it to you on Slack when I have a chance, if that's okay.
Yeah, please. Yeah, the book that I'm talking about is An Introduction to Statistical Learning.
Yeah.
Yeah?
Yep,
Okay,
no
perfect.
problem.
Thanks a lot.
Yep.
By the way, would it be possible to do that for every module?
Yes, sure.
Yeah.
I can just I believe that this particular module, LCR, is chapters 1 to 5.
Mhm.
But I'll confirm.
Yeah, please. Thank you so much.
Yep. Okay. So also we need to meet this assumption of normality of errors. So errors, in this case, these are residual. So these are the difference between the predicted values and the actual values. These should be approximately normally distributed. And this is particularly important for conducting hypotheses tests with regards to model coefficients. So after fitting the model, what you can do is you can get this quantile, or QQ plot to check for normality. So in a QQ plot, if the residuals fall along the sort of straight diagonal, this suggests that they're normally distributed. And if the points deviate significantly from this line, this might indicate that the residuals are not normally distributed. And while this assumption is important, we'll see in the plots coming up that there are sometimes often small deviations from normality. And these usually aren't a major issue, especially with larger sample sizes. So some deviation's okay, but substantial deviation, that's when it becomes an issue. So ultimately testing these assumptions, you get confidence in your regression model, that it's reliable and that your hypotheses tests are actually valid. So these are all assumptions that need to be met in order for your results to be interpretable. Okay, so here's an example of this plot of residuals versus fitted values. So here, fitted values are these predicted values for our Y variables. So for example, here, the predicted values for house price from our regression model. And these predictors are what the model estimates as the expected outcome based on our predictors. We also have residuals, and once again, these are the differences between the actual values of Y and the values that our model predicted. So in other words, residuals measure how far our model's predictions are off from the actual data. So in this plot, we have this horizontal line at 0, and this is representing where the residuals should be centered around. So as the ideal residuals should be evenly distributed around 0. And if the points are randomly scattered around the 0 line with no discernible patterns, this would suggest homoscedasticity is met, meaning that the variance in residuals is constant across all values of x. So across all predicted values of y, we get this sort of homoscedasticity, meaning we don't see any patterns. If we were to see this funnel shape, so meaning that if they were centered around 0, and then also, for example, as the house price prediction increased, we also get larger or smaller errors, this would indicate that there's a violation in homoscedasticity, and it would suggest that the variability in residuals is not constant. So here, this is a plot that's often used to assess whether homoscedasticity holds and also ensures the reliability of your regression model. And we also have the second plot that I mentioned, this QQ plot, and this is useful for checking normality of residuals. And this plot, once again, is comparing the distribution of your residuals to a normal distribution that would follow this red line here. So if the residuals are normally distributed or roughly normally distributed, the QQ plot will align closely with the straight line. And this would suggest that the residuals follow a normal distribution, satisfying this assumption. However, if the points bend away from the line, either above it or below it, this would indicate that the residuals are not normally distributed. So perhaps there's some skewedness where residuals are not symmetrical, or there's heavy tails where on extreme values of y, this is where this assumption is not met. In practice, however, these small deviations like you see here from normality are common, and they don't drastically affect the results. But for example, if you had a QQ plot that showed significant deviations, so if it looked something like this, this would warrant further investigation and determine the influence of the model. So perhaps your data is not normally distributed. Okay. Does anyone have any questions? Okay, awesome. Was someone turning on their mic?
Yeah. Sorry, I was just trying to ask a question. Like,
Sure.
so I still didn't get the QQ plot. Like, so you're plotting I understand the residuals, and so on the x-axis, can you just go back to that? Like, so
Yeah, so the main idea from the QQ plot is that this straight line here is
Yeah.
this sort of theoretical normal distribution. So this is if your data was normally distributed, it would go along this red line. And we're basically plotting the residuals against it to check whether or not there's deviations from this red line. And if there are, that would indicate that perhaps our residuals are not normally distributed.
I get that, but I just thinking practically, how do you make this plot? Like, so you have this the residuals from comparing against the true value, the estimated value, and then are we now using the mean and the standard deviation to create and like a normal distribution out of it, and then plotting it against in quantile way, or you're doing something else like in
Let me see if I can find a quick reference for you. Honestly, oftentimes, especially within Python, there's already like pre-existing packages that do this. Like we'll see it within the slides. There's like literally a line of code that already creates these plots for you, and you just sort of plug the residuals that you obtain from your model in, and it outputs something like this.
Okay.
But maybe I can find something.
Because I was trying to understand the theoretical quantiles, like what does it really mean? Like because I myself have done probably done these things myself, but I also never spent time to really understand it. But it's okay. I can look it up.
We'll take 10 minutes now. In the meantime, I'll see if I can find any good resources that maybe I can share in the chat as well.
Sure. Yeah. Thanks so much.
Yeah. Okay, so it's 6:55. We'll come back at 7:05, and then for the second half, we're gonna jump to Jupyter Notebook and do some live coding together. And yeah, just for those of you asking, the slide deck and also the pre-filled Git notebook are all available under O4 this cohort. They're separate from sort of the required material just because this is optional material. So that's why it's in a separate folder, but it is available. Okay, so we'll come back at 7:05 to do some live coding. Okay, so it's 7:05, so we'll get started again. So right before the break, we mentioned that we're gonna now flip over to our Jupyter notebook for some live coding. Just as a reminder, the pre-filled notebooks are available on the repo, but you also have um, access to, so you also have access to that, but I always encourage you to join me for live learning. And in this session, we're going to continue working with a data set of real estate transactions from Sacramento, California, just as we did with the regression portion of this module. So just as a reminder, this data set has features like property location, the size of the house type, etc., and the target variable is house price. So this is what we aim to predict, or a response variable. And as always, our first step is going to be importing our libraries. So import libraries, and these are the libraries. I'm also going to copy and paste it into the chat for you guys. These are the ones that we're going to be working with today. Okay, so in our previous sessions, we discussed that linear regression aims to find basically the line of best fit. So the line that minimizes the sum of square differences between the actual data points and our predicted values. And this method works well when there's a clear linear relationship between our predictor variable and our response variable. However, even when the data is randomly scattered without any sort of trends, linear regression would still attempt to find the sort of line of best fit. And this happens because linear regression doesn't assume any specific relationship between the variables, and instead it really just focuses on finding a line that minimizes the residuals or the errors. So even if that line doesn't follow this linear pattern, the algorithm will still generate a line that sort of fits the data by basically just minimizing the squared errors. But this line may not offer any meaningful insights into the relationship. So what I mean by this is even if the data is scattered without any clear trends, the line produced by linear regression might not reflect the actual nature of the data. And in these cases, the line could give us this false impression that there's a linear relationship between X and Y when in fact there's not one. So that's why it's really crucial to test the significance of these fitted lines, particularly the slope of the coefficients, to determine truly if this is representing a significant relationship between predictor and response variable. And this is when we get into hypothesis testing, which basically tells us whether the slope of the line is significantly different from zero. And as a reminder, if it is significantly different, this suggests that there's a significant linear relationship between the predictor and the outcome. However, if the slope is not significantly different from zero, it would imply that the linear model may not be a good fit for our data. So just as before, our research question is inferential this time. Is there a relationship between the size of the house and the price of the house? And to determine if the relationship between the predictor and the response variable is statistically significant, that's when we need to perform hypotheses testing. So before any calculations, I'm just going to define two competing hypotheses. So I'm going to define our null, which is no significant relationship between house size and house price. In other words, beta 1 is equal to 0. I'm also going to define our alternative hypothesis where there is a significant, I'm going to put linear as well, significant linear relationship between house size and house price. In other words, beta 1 is not equal to 0. Okay, so with these hypotheses set, now we can test whether the slope coefficient or this beta coefficient is once again significantly different from 0. And this helps us determine whether there is this meaningful relationship between house size and house price. So our first step is going to be simply just loading in our data, just as we've done before. We're going to call it Sacramento, and we're going to use pandas read CSV function. So pandas read CSV, and it's stored under data sets, just as we've done before, and Sacramento CSV. So this is what our data looks like now. Okay, so this is what our data looks like, same as before. Given our research question, we can see that the columns we're interested in are this column square foot, which represents the house size in square feet, and then also price, which is the house price represented in US dollars. So before doing any modeling, we're just going to simply plot a scatter plot between X and Y. I'm going to copy and paste this into the chat as well. So here we have this scatter plot. So we have house size on the x-axis and house price on the y-axis. And the scatter plot is showing us the linear relationship. So as the house size increases, we see that the house price tends to increase as well. And this observation satisfies this assumption that we talked about of linearity, which states that the relationship between x and y must be linear. So our other model assumptions were independence of observations and multicollinearity. So the assumption of independence would require that the observations in the data set are independent of one another. So we talked about the fact that each house listing should represent a unique independent listing. And as I mentioned before, this is more so built into how the data is collected. So for example, if data points are representing individual house listings, the price of one house shouldn't affect the price of another, which is something that's once again built into the data that we can't necessarily test for. And then multicollinearity would only occur with two or more predictive variables being highly correlated, leading to redundancy within information. But since we're only looking at one predictor variable here being house size, multicollinearity really isn't a concern for us. Okay, so all the before model assumptions have been met, and now this is when we can begin modeling our data. So I just also want to really briefly highlight the fact that we're not going to be splitting the data into train and test. So when we split our data into train and test, this is a standard practice for predictive modeling. So here in predictive modeling, once again, the goal is to generalize performance of a model. However, what we're doing today is not predictive model, we're doing inferential hypothesis testing. And here, the primary focus is on understanding the relationship between variables and making population level inferences rather than predictions. So once again, for hypothesis testing, our goal is to estimate population parameters like these regression coefficients and assess their significance. So here we're using the entire data set, and this provides us with the most precise estimate of these parameters by leveraging all the available data that we have. If we wanted to check the robustness of the model in terms of prediction, then yes, this is when we would split the data or do cross-validation. This is when those methods become ideal. However, this particular approach that we're talking about today doesn't provide insights into prediction, but it's more so statistical inference or of the relationship, which is the goal of inferential testing. So really the key here is that inferential hypothesis testing, we work with the full data set to derive the most accurate and reliable estimates of the relationships. But if we were planning to do any prediction-oriented tasks, that's when we would split the data. So I just want to clarify that because sometimes that's a point of confusion. Does anyone have any questions about that? Okay. All right. So to perform such a simple linear, oh, yep.
Sorry, I just remembered like on the last assignment that we are doing like so we could first of all we could like use like individual predictors instead of taking all the predictors in once, right? And sometimes you see that we get a very strong relationship, but when we combine all of them, like multiple predictors, multiple variables to predict the response variable, we see that you get a different beta coefficients, right, for
Yes.
each of those predictors.
Yeah.
And
Well, you have to
whatever,
keep in mind that when you have multivariable linear regression, your beta coefficients are changing because remember you're saying the beta coefficients reflective of the change in y per the unit change in your specific variable, holding the other variable constant. So we talked about even the number of bedrooms in the house size example, and how some people were like, well, that's weird that the beta coefficient was negative. But perhaps it was negative because you're holding house size constant. So you're looking at either more bedrooms or less bedrooms of a same size house. So you have to take into consideration all the variables, if that makes sense.
Right. So that means that the relationship can get actually weaker than if would have been just that
Yeah. Yeah.
variable. And that's okay. I mean, that's what is
Yeah.
expected, right?
Yeah.
Okay.
And beyond the scope of this particular module, but if you're interested in that same textbook, I forget what it's called.
Statistical learning.
Yeah. So in the next, so this module goes from chapters 1 to 5, but in chapter 6, it talks about choosing the best predictors and also like stepwise adding predictors or removing predictors to get sort of the best model. Yeah, so beyond the scope once again, but that's sort of advanced linear regression techniques as well.
Okay. Yeah. Thanks, Julia. I appreciate
Yeah, no problem. Okay, so to perform simple linear regression, we use the stats models package in Python. So stats models is a really powerful library designed for statistical analyses and modeling, and it provides us with valuable tools for fitting models, performing hypotheses testing, really making it a go-to in terms of statistical modeling and inference. So one of the key features of stats model is its formula interface. And it basically allows you to specify models using formula syntax. So I don't know if any of you are familiar with R, but the syntax with this package is very similar to the syntax in R. And this syntax makes it really easy to define models and interact with your data, as you'll see. So the overall model syntax for linear regression in this particular package looks something like this. So I'm just going to make a comment. It's basically the model, and then within parentheses, you have your response variable, and then this tilde, and then the predictor. And then you give it the data, and then dot fit. That's basically the syntax. So another thing I just want to highlight is this particular package uses ordinary least squares, or OLS, for linear regression. And OLS is basically a method for finding the best fitting line in your data points. So imagine you have this scatter plot with all the data points and you want to draw the line that best captures the overall trend. OLS is a method to help you determine this by determining both the slope and the position of the line that minimizes the total distance or errors between the data points and the line that you're drawing. So basically you can think about it as trying to draw a line that gets as close to all the data points as possible without getting too far away from any of them. So it's really minimizing the distance between your line and all the actual data points. And OLS basically achieves this by adjusting the line ever so slightly so that the sum of the square differences between the observed values or actual data points and what we predict based on the line is as small as possible. And this relationship is most accurate for explaining the relationship between these variables. Okay, so now that I've basically explained the syntax, when it comes to running our model, it'll look something like this. So I'm going to define it as variable model, and then we're using this package that I mentioned called SMF, and then it's the OLS model as I just mentioned. And then within the parentheses, you have price, which is our response variable, and then this tilde, and then also square footage, which is our predictor variable. And then we also have our data, and if you recall, we're using the Sacramento data. And then at the end, we're just using dot fit. So we're using the fit method to fit our model to the data. Okay, so we run that, and then once we fit the model, we can view the model summary using model.summary. So we're using the summary method. Yep, there's a hand.
Yes, so I want to ask, this linear regression, is it for the inferential hypothesis testing or is for the predictive?
Yes. So this particular package is for inferential statistics. Yep. Okay. Sorry, I just want to use the parent. Okay, just to make it look nicer. Okay, so this is what our output looks like. And I just want to share my screen for a second. I'm going to switch screens. Okay. Oh, no. You guys can see my screen now, right? Yeah, okay, perfect. Okay, so this is what the model output looks like when we write print and then the model summary. So they'll generate this really detailed output with several key statistics that help us assess the quality of the regression model. So we have the coefficient, which is this column here, and these are the estimated beta values for the intercept and slope of the regression line. We also have the standard error column, and these represent the standard errors of the estimated coefficients. So here, the smaller error would suggest a more reliable estimate of the coefficient. We also have the t-statistics. So these t-values tell us how many standard errors the estimate coefficient is away from 0. And then this p-value, this column next to it, is helping us assess whether the coefficients are statistically significant. So if the p-value is below a significance level, often 0.05, the coefficient is considered statistically significant and statistically significantly different from 0, suggesting that there is indeed a meaningful relationship between this particular predictor and the response variable. There's also other things here, like for example, there's this R² value, and this tells us how well the model has explained the variance in the response variable. So in this case, how our model is explaining house price. So here, values closer to 1 would mean that the model explains complete variance. Values closer to 0 would mean that the model doesn't explain much variance. And then we also have these confidence intervals here, and these just show the range of values in which the true confidence interval might lie, coefficient, sorry, might lie. So remember, these are estimates based on the sample, but we also have these confidence intervals that are saying the true beta coefficient will likely lie between this range. And if the interval does not include 0, this is also indicative that the coefficient is statistically significant. So this is sort of the summary output, and I just wanted to summarize sort of where we're pulling these values from. So for example, this intercept coefficient would be our beta naught, or our square footage coefficient would be this beta 1. And then we have these corresponding standard errors for beta naught or beta 1. And then from this, we can extract a regression equation. So for example, our predicted value of price is equal to beta naught plus beta 1 times x. So in other words, here it would be, for example, 16,200 plus 134 multiplied by our predictor, which is square feet. And then also, I'm just showing here these equations that we talked about, how to get the t-values for both the intercept and the square foot. So basically, by plugging in our beta coefficients, comparing it to the value under the null hypothesis, which is 0, and then dividing it by the standard error, we get both the t-value for intercept and t-value for square root. And this model does all the heavy lifting in the background, but it's basically showing us that t-values greater than this t-critical value will give us a p-value of less than 0.05, representing the fact that they're statistically significant. Yeah, there's a hand up.
Yes, sorry. So I was just wondering at the significance value for the slope. I see that it is 0. So as a significance value cannot be lesser than 0, if I understand right. The 0 is like a very, very, very highly significant in this case, or
yeah, it would be like 0.0000. Yeah.
Okay,
Yeah.
okay. So it is very highly
Super significant. Yeah, and you can visualize that here. Like for example, the shaded regions, the t critical, and this is where the t value of 30 would be.
Oh, I see. Okay, so it is like
Super
very, very
significant.
low value. So it is effectively kind of 0. Okay.
Yes. So I just wanted to sort of annotate what the expected output looks like. This slide is also available for you on the Git repo as well, but these are just key things to look out for. I'm going to switch back to the live code now and also check the chat to make sure everyone's all right. Yes, I'll share this in the chat as well. There you go. Does anyone have any questions about this? We all okay? All right, awesome. Oh,
Julia, just a quick
yeah,
question. I know this procedure requires OLS to fit the model.
Yeah.
Is OLS, I'm not quite sure exactly what OLS does, but I know it's a kind of linear regression
yeah, it basically
analysis.
just finds the line of best fit that minimizes the distance between the actual values and the line.
Right, and I understand that OLS is a particular kind of regression analysis, and then it has
Yeah.
to have specific assumption met, correct, in order for this to be performed.
Yeah, so we covered the assumptions. Yep.
Okay, thank you.
No problem. Okay. So the last thing I want to highlight also is the F statistic here, which is quite large. And then there's also the corresponding p-value underneath, which is super significant. So this indicates also that this model is a better fitting the data compared to a model that would just predict the average price for all observations. Okay. So after fitting the linear regression model, we can evaluate these sort of key assumptions surrounding homoscedasticity and normality of error that we talked about in the slides, just to see or ensure that the model is actually valid. So for homoscedasticity, which is, if you remember, just means the spread of or variance of residuals, it should be relatively constant throughout all of the fitted values. And we can basically plot the residuals against our fitted values. Reminder, fitted values just means our predicted Y value. So here our predicted price. So I'm just going to copy and paste this code into the chat as well with regards to the plot. Oops. Okay. So this is what our plot looks like. And here we can see that the spread of the residuals is constant. So basically the assumption is met. And then also for normality of errors, this just means that our residuals should be approximately normally distributed. And we talked about this idea of QQ plot in the slides a little bit. So we're going to use the QQ plots to basically plot this theoretical distribution. So in this case, the normal distribution against our residuals to see if they do indeed follow this normal distribution. So the straight line on this QQ plot would be indicative of normality, and any deviations from this red line would suggest deviations from normality. I'm also going to copy and paste this plot into the chat as well. This is what I was referring to earlier when you see that, for instance, this is just one line of code representing our residuals and then our line here of normality. Okay, so here we can see in this QQ plot that most of the residuals do align closely with the reference line, indicating that normality is met approximately. There are some deviations that we talked about along the tail here, suggesting that there's minor departures from normality, but I wouldn't say this is anything too concerning. If it looked something like this, then it would be more of concern. Yeah. Question?
Yeah, I just wondering, is it, are we able to relate between the QQ plot and the residual plot? Because I see that the QQ plot deviates at a later time point, and you see more dispersion or like a deviation from the horizontal line. So is there any kind of correspondence between these two plots?
So this is also our sample data. So you can, the same thing that's shown on the y-axis here is shown on the x-axis here as well. So you can see, for example, as they're larger fitted values, it becomes less concentrated towards 0. Similarly, as we get larger values, we see more deviations from normality. So perhaps as the values that we're predicting get larger, we see these deviations from normality. Yep.
Oh, I see. I think I should have flipped the axis then.
Yeah.
Made more sense.
Yeah.
Okay, thank you.
Okay, so we can also extend this model to include multiple predictors, just as we talked about in the slides as well. So let's say we want to consider now both the house size as well as the number of beds. To do this, we just simply add a predictor to our model, and it's really easy. We just use the plus sign. So here I'm going to make a comment saying multivariable linear regression, and I'm going to call it model. So we're using the same package with the OLS function. And here we have price as our Y, and then this time we have square feet as well as number of beds as our predictors. And our data is still Sacramento, and we're still using the fit method to fit our model to the data. And then we're going to print out a summary of our model. Okay. So from our summary output, we can see that now we have square footage as this first predictor, and then we also have number of beds as the second predictor. So in terms of the coefficient for square footage is 156.23, and this means that for every additional square foot, the price increases by approximately $156, holding the number of bedrooms constant. And this means that if we were to compare two houses with the same number of beds, the one with higher square footage would be valued more, basically. We also have the standard error, and here the standard error is like 6.28. And this would suggest that the true price increase per square footage could vary plus or minus 6.28. And this is relatively low level of uncertainty with regards to this estimate. We also have the t-value that we computed. So here the t-value for square footage is 24.887 roughly, which is quite a large t-value. And this is indicative of a very strong and statistically significant relationship between house size and price. The p-value is also supporting this too. The p-value here is super small, confirming that the relationship between house size and house price is significantly, statistically significant, not due to random chance. And we also see this confidence interval here as well. And this means that we're 95% confident that the true price increase per square footage falls within this range. And we see that this range doesn't include 0, once again showing that it is indeed statistically significant. Moving on to the second predictor, so this number of beds, we have the coefficient here being, I think this is like minus 22,000, I think. Meaning that each additional bedroom is associated with a decrease in value of $22,000 roughly, holding square footage constant. And this means that when you're comparing two houses that are the same square footage, adding one more bedroom would decrease the value of the home. And then we also have the standard error here as well. And the standard error is $4,770, which is larger than the standard error for square footage. And this is indicating that there's more uncertainty with regards to this estimate of the beta coefficient. We also have the t-value here, which is 4.799, which is still statistically significant, but the effect you can see is much weaker compared to square footage. And then the p-value is also quite small, indicating that it's statistically significant. And the confidence intervals here are shown as well, meaning that for a number of bedrooms that the true value lies somewhere between this value, this lower bound, and this upper bound. Okay, and we also have the adjusted R-square. So when we have more than one predictor variable, we look at the adjusted R-square rather than the R-squared. And this is saying that there's 54.3% of variance in house price explained by these predictors. So adjusted R-squared is particularly useful when we have more than one predictor because it takes into consideration both the goodness of fit as well as the complexity of the model. So it basically penalizes the model for having multiple predictors, because unlike the regular R-squared, where as you add more predictors, obviously you would explain more variance, this penalizes the model to make sure that it's also not complicating it. So this makes it a more reliable measure for evaluating model quality and to avoid overfitting compared to the conventional R-squared. And then we also have this F statistic here. So here the F statistic is 482, and it's connected with a really small p-value as well, showing that overall the model is highly significant. And so this means that the combination of house size and number of bedrooms as predictors significantly improves our ability to explain house price compared to a model with no predictors at all that would just predict the average price across all observations. Yeah, Antonio?
Question regarding what you were describing about the adjusted R-squared parameter. Did you mention that there is some penalty system embedded to do not overcomplicate the system?
Yeah. So
Okay.
what happens
I
with
will understand that. My question, meaning coming from, I've seen this concept before, let's say, but my question is how here it will actually make the system less complicated.
So not that it makes the system less complicated, but it penalizes for additional predictors. So the way R-squared is computed is that the more predictors you add, the more variance is going to be explained. That's just a fact. But we don't want to overcomplicate a model, so as a result of that, we're adding an additional penalty sort of component. So this is saying it's taking into consideration goodness of fit, but also the number of predictors. So it has this additional penalty where the more predictors you add, it adds a penalty to it. So that way we're not taking the most complex model and compared to a more simplistic model, for instance. So we tend to look at adjusted R-squared when we have more than one predictor variable.
Okay, I understand now. So it's with 10 more predictors, R-squared will be much bigger. I'm just making it up.
Yes,
So
exactly.
adjusted one incentivize us
Yes.
not to believe that we're, yeah. Okay, thank you.
Yeah, no problem. Okay. So let's say we're also interested in house type, which was that categorical predictor that we talked about before. So let's just first really quickly refresh our memory. Let's look at the unique values that are associated with house type. So we have our Sacramento data set, we have our type column, and let's just look at the unique values. Okay, so we see that we have residential homes, multifamily homes, and condos. These are the three unique categories within house type. So to use this categorical variable in a linear regression, we need to convert it into this numeric format. So we need to do this one-hot encoding that we talked about last class. So this method, once again, is just basically converting this categorical variable into a series of binary zeros and ones, representing each category. And this ensures that the model can interpret the variables correctly. So we're going to use Panda's getDummies function, just as we've done before, to perform this one-hot encoding. So we're going to create a new data frame called Sacramento encoded, and we're going to use our Panda's getDummies function, providing it with our data set as well as the specific column that we want to convert, so the type column. And then also we're going to specify that we're just going to drop the first one as true, and that's going to act as our reference category. Okay, so now if we scroll all the way to the end, we see that we have type multifamily, type residential, and then our reference category would be condos. And reminder, we're dropping the reference category just to avoid issues with multicollinearity, and we're still able to retain all the information. Because if multi-type was 0 and residential was 0, we would know that this particular listing would be a condo, for instance. We're not losing any information. Okay. So within our type variable now, it's properly encoded. We can move on to fitting our linear regression model. And I just want to point out that because of the particular syntax that this library uses, we're just going to replace the hyphens. Like for example, here it says multifamily, it's hyphenated. We're just going to replace it with an underscore just to avoid potential issues when we're referencing the columns within the model syntax. So these libraries like stats model column names with hyphens may cause syntax errors when we use these model formulas. So that's why we're just replacing it now. So I'm just going to rename the column to replace the hyphen with underscore. Does someone have a question? Okay. So we have our Sacramento encoded columns. And so we're basically just going to take all of the columns and use a string method called string replace. And we're just going to replace the hyphens with an underscore. So that's what this line of code is doing here. So we're taking all of our columns, we're using the string replace method, and we're saying take all these hyphens and replace them with a underscore. Okay, great. So now that we've organized our data, we one hot encoded it. Now we're going to be able to model this new column. So now we're going to model these types. So we have our now categorical model. I'm just going to call it multi-cat model. And we're using the same package. So the SMF package, we're using the OLS function. And we're providing it with the price, which is our Y variable. Now we're going to have square footage, which is our one predictor variable. The number of beds is another predictor variable. Now we have type multifamily. And then we also have type residential. And then we're going to provide it with our data set, which was Sacramento encoded now. And then we're going to fit the model to our data using the fit method. And then we're going to use the print function to print out a summary of our model. I'm just going to copy and paste this into the chat as well, just because it's a bit long. Okay, so in this particular model, we have one category that's a reference. So here we have condos as the reference category. And this is automatically chosen just because we dropped the first column. So the reference group, once again, does not have its own coefficient in the output. Instead, it effects are reflected through the coefficients of these other categories. So these beta coefficients are in reference to this other category. And basically showing, for example, how house price differs from this type in comparison to condos, as we talked about. So here, once again, condos is chosen as the reference group, and the coefficients for multifamily residential are telling us how the house price differs from these particular house types relative to condos. Okay, so I'm just going to focus on these two rows now. So this first row is representing multifamily type homes. We have this coefficient, which is, I think, minus 12,000 roughly. And this means that on average, multifamily properties are expected to be $12,000 less expensive than condo properties, while keeping these other variables like square footage and number of bedrooms constant. We also have the standard of error here, and this is, I believe, 27,000, and this indicates that the actual price difference could vary plus or minus $27,000. And this is a pretty high level of uncertainty with regards to this estimate. We also have this t-value here, and this t-value is minus 0.45, and this is pretty small, pretty close to zero. This suggests a weak relationship between multifamily properties and house price. And in fact, if we look at the p-value, we see that this p-value does not cross the threshold of significance, indicating that the coefficient is not statistically significant. And the price difference between multifamilies and condos is likely due to random chance. So it's not significantly different. We don't have sufficient evidence to reject the null. We can also look at this 95% confidence interval as well. So here we can see that this range does indeed include zero. And it reinforces the conclusion that the difference in price between multifamily and condo price properties is not statistically significant. We also have this residential type homes. So this is the second row here. So here the coefficient is, I believe it's $36,000 roughly. And this means that residential properties are expected to be on average $36,000 more expensive than condos, holding these other variables like square footage and number of bedrooms constant. And then we also have the standard error, which is roughly $13,000, indicating that the true price difference is either plus or minus $13,000, perhaps a moderate level of uncertainty. We have this t-value here of 2.68, and this is large enough to indicate a meaningful relationship, as we can see by the p-value being less than 0.05, indicating that there is a meaningful relationship between residential properties and house price. And then looking at this confidence interval, we do see that the confidence interval is roughly between like 9,800 and then roughly 60,000. And since this interval does not include 0, it further supports the conclusion that price difference between residential homes and condos is indeed statistically significant. So that's how you would interpret this model output with regards to categorical variables.
Sorry, again.
Does anyone have any questions?
Yeah, sorry, Julie. Regarding the type multiple family, for the 0.647, this would can you please explain that again?
This is the p-value. So this is, remember, a p-value, if it's less than 0.05, it would mean that we can reject the null hypothesis. But if it's greater than 0.05, that means that we don't have sufficient evidence to reject the null hypothesis, meaning that there's not a significant relationship.
Okay, got it. Okay.
Yep.
Thanks.
Is there another hand up?
Yes. So scrolling down on the summary, I also see that there is a message saying that the condition number is large and there might be a strong multicollinearity in this sort of data set. So
Yeah.
I was wondering what would be the approach one can do in this sort of situation? I guess this is something needs to be attended to, right?
Yeah. So if you identify high multicollinearity within your model, you can do one of two things. You can either remove one of the variables because perhaps they're contributing redundant information, or you can combine them. Like we talked about the example of rather than square feet and beds as separate predictors, perhaps we can combine them as a ratio of number of bedrooms per square footage, for instance.
So it has to be like a trial and error approach, like you try to reduce the predictors like one by
Yeah,
one.
so you can identify which predictors are have high multicollinearity. For example, I believe the same thing appeared when we just did the 2 as well, so you can see, for instance, square footage and number of beds, it has strong multicollinearity. So perhaps we would either remove one of them because they're providing redundant information, or we can combine them to do, like, for example, number of beds per square foot.
Okay.
Yep.
Right. Thank you.
No problem. Yep, Omar?
Yeah, Julia, could you go back to the last table
Yeah.
or the last model over here? So I'm just gonna ask the obvious over here. Look at now, say if I wanna train models and start comparing and stuff, does this mean that I can drop the type multi-family because there's no relationship?
So there's multiple different ways to do this. Like there's stepwise ways where, for example, you have the best subset selection where you compare. It sort of goes beyond the scope. So there's stepwise. So you start off with all the predictors you have and then slowly pick off one by one until you're left with the most simplistic model that explains the most variance. Alternatively, you start with one predictor and then you keep adding them to see if they're offering significantly more explanation of variance. So there's multiple different ways to do this that go beyond the scope of what we're going to talk about. But I will say for reference that they are available, I believe, in the textbook ISLP in chapter 6. There's a whole chapter on sort of variable selection and how there's different methods to do this.
Okay. Got it. Okay.
Yeah.
Cool. Thanks. But this one over here is a valid. I mean, what I said is valid, right? That's one of the reasons that we would basically just scope it out, let me say, for the multi-value.
Yeah. So oftentimes as well, people use ANOVAs, for example, to compare models. So you're comparing, for example, a nested model. So one with 1, 2, 3 predictors, and then one with 4 predictors, and seeing if they're statistically significant in terms of the amount of variance they're explaining. And if they're not, you always go with the more simpler model. So the one that you, for example, you remove the variable. Yeah.
Okay. Got it. Thanks.
Yeah, no problem. Okay. So that's all we have with regards to this new additional content. Does anyone have any further questions about this?
Sorry, Julia, just a reminder for the references in the textbook, right? You said that
Yeah.
you're gonna share that. Uh-huh.
Yeah, I can link it in the
Okay.
chat as well. It's a great textbook that goes a bit more in detail with regards to math.
What I'm saying is, I'm just reminding you with what you told me before that you're gonna
Yeah.
find all the chapters. Okay, got it. Okay,
Yes.
perfect.
Yep.
Thanks.
Can you just actually Slack me just so I don't forget after class, just to be like, just as a reminder,
Sure.
please.
Yeah,
Thank you.
perfect, thanks.
Okay, so that's all we have with regards to this module and content. So I really appreciate how attentive you all were. And I acknowledge that this is a steep learning curve, especially for those of you who didn't have a super strong, perhaps statistical background. So thank you so much for staying on board with me until the end. And it was a great opportunity to work with you all. Yeah, that's all we have for today. I'm just going to stop sharing my screen. And I'm going to stop recording now. There is office hours until 9 o'clock today, and then there's a work period both tomorrow as well as Saturday if you need any help with your assignments.